Figuring out how our universe will end is as dark a mystery as the Big Bang. It could collapse back in on itself, like a balloon when the air is let out.
Cosmology is concerned with the big questions of the universe, which are frequently the same questions that keep philosophers awake at night. When did the universe come into being? How did it all begin? Is it true that the universe has always been expanding? For the record, the answers are approximately 13.8 billion years ago, in a high-density state that rapidly expanded, known as the Big Bang. And yes, but not always at the same rate. But there's one thing they haven't figured out. How will this all end? It's a big question, to be sure, but we've made surprising progress towards an answer. In the late 20th century, the astrophysical community was stunned to learn that the universe was tearing itself apart. Scientists have known for decades that distant galaxies all move away from us, with the farther ones moving the fastest. This makes sense only if the universe itself is expanding. Given all of the matter in the universe, gravity should be slowing down the expansion. However, when cosmologists calculated how much it has slowed, they discovered that the universe's expansion has accelerated. Because no one knows what is causing the acceleration, cosmologists have dubbed the mysterious dark energy. It is so dominant, about 69% of the total content of the universe, that it quickly became a part of any discussions about the universe's ultimate end. While there are no definitive answers, those discussions have yielded a few intriguing possibilities. The Big Rip. Because no one knows what dark energy is, we cannot predict how it will behave in the future. Dartmouth College's Robert Caldwell proposed a new theory of the universe's expansion in 2003, in which the rate of acceleration increases over time. Consider a driver who keeps his foot on the gas pedal of a car that has no top speed. The car would eventually fly apart in pieces as friction took its toll as it got faster and faster, with the speed of the velocity change itself increasing over time. A similar thing happens in a universe with constant acceleration. Galaxies are destroyed, the solar system disintegrates, and eventually, all the planets disintegrate as the rapid expansion of space rips apart its very atoms. Finally, our universe would explode in an explosion of literally infinite energy. According to current theories, if the so-called Big Rip is in our future, it will take another 22 billion years to arrive. However, many details remain to be filled in, and scientists such as Vanderbilt University's mathematician Marcello Visconti will do so. His early research concentrated on bulk viscosity, the measurement of a fluid's resistance to expansion or contraction, and how moving fluids behave as they approach the speed of light. This can occur in extreme astronomical circumstances, such as an exploding star. No one had previously successfully modeled how a viscous fluid would behave at relativistic speeds, but Visconti did so in collaboration with colleagues in the Vanderbilt physics department. For decades, scientists have tried to connect mainstream physics understanding of viscosity with a related concept, cosmic viscosity, which explains the universe's resistance to accelerating expansion. Visconti's work was instrumental in beginning to understand cosmic viscosity because the universe is modeled as fluid on large scales. For the first time, he demonstrated that the driving force behind the Big Rip, if it occurs, could be the universe's cosmic viscosity. The results are fascinating, but Visconti admits that Big Rip theories still need some work, particularly the part about infinite energy being released. Finding an infinity in physics is likely an indication that we are missing a piece of the puzzle, he says. An improved theory could show that the universe's expansion rate does not reach infinity, regardless of how large the Big Rip becomes. For the time being, we'll have to wait and see, as with many cosmological theories. The Big Freeze. According to many current theories, dark energy is a cosmological constant or a type of uniform energy that exists throughout space. If the cosmological constant is the dominant thing in the universe, explains Mark Troughton, co-director of the University of Pennsylvania's Penn Center for Particle Cosmology, then instead of speeding up unsustainable and tearing itself apart, the universe will just keep expanding forever. As long as the cosmological constant dominates, the universe will continue to accelerate, and that's it. That's it may not sound like much, but it's a depressing way to end. As long as the cosmological constant drives the universe's acceleration, all galaxies outside our immediate neighborhood will be too far away to see in a few trillion years. Their light will simply never reach us. Entropy would rise as well. Star formation would come to an end in 100 trillion years, as all the matter needed to fuel it would be depleted. The universe will be a cold, lightless, lifeless place for the rest of eternity as black holes evaporate and matter decays into radiation. The Big Freeze is the name given to this bleak future. Dark energy is so baffling that it has taken nearly 2 decades to comprehend the theory sufficiently to design experiments to investigate it, let alone determine whether the Big Freeze is in our future. Of course, we wouldn't be able to do anything about it if it did. Troughton is a theorist for one such planned experiment at the Large Synoptic Survey Telescope, which is currently under construction and will imagine the entire sky in unprecedented detail every few nights. When it turns on in 2022, the telescope will study billions of galaxies every night, providing astrophysicists with unprecedented access to galactic behavior. Scientists should have enough information to finally unlock some of the dark energy secrets by analyzing how gravity affects galaxies' light and analyzing their 3-dimensional positions and movements in space. Is it the result of quantum fluctuations in the vacuum of space? Is it just another aspect of gravity that we'll have to incorporate into the laws of physics? Understanding such details is critical if we are to determine whether we are on the verge of the Big Freeze or something else. The false vacuum. Of course, there's always the possibility that dark energy will be ineffective. Other scenarios we've considered assume that our universe is the only one. But what if there's more out there, and our universe is just one part of a larger multiverse? Could the fate of these other universes affect our own? The quick answer is yes. Imagine going to a very, very large scale, much larger than our current observable universe. Cosmologist Jonathan Braden of University College London explains, while our universe is homogeneous and roughly the same everywhere, taking such a broad view may reveal that it is only a tiny pocket with its own physical parameters and laws distinct from the larger multiverse. If this is the case, our universe would be in a state known as a false vacuum, in which we mistakenly believe we are in the most stable state. But it is still possible to drop to another one suddenly. Braden explains that this would cause a phase transition, similar to how water changes from liquid to gas at its boiling point, but for the entire universe. He compares our universe to a bubble boiling in a pot of water, with each bubble having its own set of laws and constants. Eventually, these bubbles will collide, and it will appear to us as if our universe collided with another universe. That would be every bit as bad as it sounds. A collision of this magnitude would mean the end of our universe, as everything would change to a new state. It could result in a merger of the two universes, or in the creation of something entirely new. There would be no warning, and there would be nothing we could do. So that's the end of the video. Make sure to like the video, subscribe to our YouTube channel, and press the notification bell so you never miss out on our next videos. Until the next video, take care.